I'm starting now the recording for this new meeting, and it's essentially, it will be called the DEM-NUHAC 057. So I put together a few things which I thought might be provide a good background to the understanding of Poisson's formula, of the Shannon sampling theorem, and so on. So as usual, I'm starting with the definition of my lattice constants, maybe to make sure that you have everything in the document. I'm setting what people would call a Dirac, engineering people would call a Dirac comp. A Dirac comp is an indicator function of a subgroup in our case. A is a divisor of n. And clearly, if I step from the first component, recall this is representing omega to the 0 on the unit circle, then you have 24 positions at distance 20. And so a cheap way to put these ones into the matrix is just by this command. So it's understanding that if you put in a vector position and on a vector of indices one value, you put the constant value. So correctly, so to say, the original version of Matlab, you had to put ones of length of size 1 to n over a, but now the constant is. And the stem command is, of course, in this case better than the other command. Plot, because plot would make a connection of these things. Now, I'm not sure if that works, but we know that a function which is periodic is actually can be viewed as a function on the unit roots of order n, and that means that we would have functions whose graph is glued on a cylinder. Now, I'm not sure if this fancy, yeah, okay, you see it, it's working here. So in a standard Matlab M routine, you would be able to rotate this. I don't want to play around, but in this way, you see there are always 19 components which are 0. And it's periodic, and because A is a division of n, it's really periodic. There is no jump or discontinuity, and that's why I think it's good to have this. Now, if you look at the Fourier transform, and recall that essentially the Fourier transform is taking this set of coefficients on the unit roots of order n again. So maybe as a good exercise for yourself, take the sequence, the Shah distribution of order 8 with distance 2. That would be, you're looking at polynomials of degree 7 and evaluating it on the unit roots of order 8, because degree 7 means, of course, 8 coefficients. So what is the polynomial that would correspond to such a Shah distribution? That would be 1, which is 0, which is omega to the 0, so constant, 1 plus x squared plus x fourth power plus x sixth power, because x to the 8th power would be already the 0. Now, if you evaluate this at the unit roots of order 8, you see quickly that you're getting sometimes a 1 and sometimes a +1 and a -1, which is canceling out. So exactly at those two positions, our sampling rate is 2, and now we have two positions where we get the 1. We would have 1 plus 1, and here it's 24 positions. Now it's 20 positions, so we have A equal 20. We have now 20 positions, and at each of those 20 positions, each term, each evaluation of our pure frequency would give a 1. So it's not so surprising that you get a value 24, which is n over A, and that you get 20 copies. So you can also say, well, you know that there is a fixed relationship between the L2 norm of this function. What is the L2 norm of this? Maybe we also compute it. Maybe I'm inserting this. So what is the norm of this Shah? Sorry, SHA is because of the Greek letter. Also, engineers call it Dirac comb. And well, we have seen that there are 24 such positions. And in order to be faster, I tell you, of course, the L2 norm of a sequence which has 24 ones is 1 squared plus 1 squared plus 1 squared 24 times, and then you take the square, so it must be this here. And clearly, what we see here, the norm of FFT of this SHA distribution, we know it will always be, maybe I'm just running it like this, will always be a multiple of this. And so we have square root of 24 was the original one. Maybe I'm jumping. Okay, so it was the wrong direction probably. Yeah, and then I should say, let's divide by square root of n, because we are one-dimensional, and we have a normalized Fourier transform, and then you will see it's okay. So you see that this explains if it's constant and if it's sitting on those 20 positions, then of course the value must be 24, so otherwise this doesn't work out. Now, the next thing is just to demonstrate something very, very general and very easy, namely that if you have an orthonormal change of basis and the Fourier transform is up to the normalization of, in the one-dimensional case, normalization factor square root of n is just a change of basis. So the usual way of thinking of this Fourier transform is we change the basis from the standard unit vectors to the pure frequencies. And again, either you think of it as a natural object with the pure frequencies being sine and cosine, or the discrete version of sine and cosine, then the absolute value of the pure frequency is, of course, 1. And each of them has the norm square root of n. So if you use the Fourier transform matrix and its transpose conjugate, which is the same as the conjugate because it's a symmetric matrix, then of course the inverse will be has to be taking care of this factor of square root of n, which is missing in both directions. So you have inverse Fourier transform matrix is, maybe this is something that I should also recall to you, but this is not, we have done this before, I guess. So if I say this is the matrix realizing the Fourier transform, so it's the matrix where each column is the image under the FFT of a unit vector. And then I would like to check whether the inverse of this matrix or the transpose conjugate, which is the same as transpose divided by n, are the same. And there should be no problem to verify this. Okay, so now what I want to recall to you in a very naive way is a unitary matrix preserves scalar product. This is actually quite clear. Maybe I'm explaining it once more, even how I'm proving it. So kind of a Matlab proof that you can put into theoretical terms. But first, let's verify. So I'm saying, let's choose two row vectors. See, there was a typo. Maybe that was a problem here. And so I'm choosing two row vectors and their Fourier transforms, and they are obtained by applying the FFT command. And then I would like to know or verify that multiplying from the right or doing the Fourier transform is the same. So that's just the verification that I'm doing the right thing. And then I'm saying now I'm looking at the scalar product. So I'm just demonstrating by a random example that the Fourier transform, being up to rescaling a unitary matrix, is preserving scalar product. Now the verification is easier if you take row vectors, because then you take two row vectors and the scalar product of the first with the second is just turn the second one from row mode into column mode. so that you have a transpose conjugate on the second part. That's what mathematicians like, and therefore this is the scalar product of the Fourier image, and then you divide by the scalar product. And when I saw the result, I was a little bit worried and said, oh, it's not 0, it's not 1 or so, n or so. Yes, because the representation of the result is in a strange format. So that's why if you look closer, the imaginary part, maybe I'm also showing this imaginary part of, well, no, I'll leave it. I didn't assign a value. So you see, this is 0 numerically, and the first one is n. So yes, this is right. But you can also say that what do you expect from the FFT? This is u times f. And then I'm saying, what is this? This is BV with f, and you do a prime. Okay, so this is giving you some number. But actually, as you know, matrix multiplication is associative, and therefore you're getting this here. And this is, of course, the same as n times identity. Sorry. And so if we compute these numbers, it's not surprising that you get always the same number. So in this case, it's really very easy. So that's actually the proof that you could write down with scalar products. Okay, now I'm also want to give you a group theoretical interpretation. So for each group, in here, the cyclic group with this red subgroup, there is the group of all the pure frequencies or all the characters which are constant 1 on the subgroup. So another way to say it, well, this was the reason why you had exactly these values. In all the other values, the values that are taken by these pure frequencies are different values, which are different unit roots of order n, with n or k, with k being 2, 3, or whatever, which means that you always have a sum over all the unit roots of order k. And if you take +1, -1, or the sum of unit roots of order 8, or even sum of unit roots of order 17, they are the second column in the Fourier matrix of size 17, which is perpendicular to the first row, which is 1, 1, 1. So the sum has to be 0. But just look at the picture of the unit roots of order n. The center of gravity of them is always the average of the values at 0, except you have 1, 1, 1, and then you have the number of points. So this is another group with now the divisor n over 20, which is 24. And this goes now into an abstract concept. So I'm saying whenever you are having a subgroup here now, just divisor, there is a complementary divisor, and this is called the perpendicular subgroup. Maybe I'm giving a demonstration also for this. And here you don't see any perpendicularity, that's also clear, but you can get it by taking the FFT and normalizing it, dividing it through the number of elements that your group has. And this is actually the way how I would compute the dual group, or whether I would, you can also say, what is the dual group of a dual group? And that's defined, that's exactly the original group. And it's like you have vectors. If I give you 3 vectors which are in the plane, you can say, what is the orthogonal complement? And in R3, you would say, well, that's a certain line perpendicular to the plane. But then what is the thing which is perpendicular to the orthogonal complement? And you would get the plane generated by these 3 elements. So the same is true here. If you have few elements in a big group, we will apply this in two dimensions, and you would generate the whole group. Then you can take those 2 vectors, take the perpendicular and then the perpendicular, and that would give you the group generated by these 2 elements. So the smallest subgroup containing these particular elements. So this is just one way that's preparing for the Shannon sampling theorem and the Poisson formula. And I will try to explain those things to you today in more detail. Now, the Shannon sampling theorem is something quite important and quite useful, mostly also for the engineers, but also in our daily life. We are using CD players or streaming services, and in order to listen to music, and if you have good headphones and a streaming device, you're thinking that it's almost like a concert hall. I mean, at least you recognize everything. You don't hear a difference or so. And all this despite the fact that you're not getting a continuous flow of information. Well, at the end from the loudspeaker, probably yes, but everything is stored by taking 44,100 samples of this original input signal. Now here in mathematics, we are dealing with complex valued functions because the mathematics is easier. And so I'm showing you in my comparison a function which is band limited, and you see blue and red as real and imaginary part. So again, think of the left upper picture to be the smooth function, which you should also think of being periodic along the cylinder. So you could do this real part plot on the cylinder again. On the right-hand side, you see that there are only pure frequencies up to a maximal frequency. I'm not sure exactly what the maximal frequency was. I don't want to zoom in, maybe, I don't know, 15 or so. Let's assume it is 15. Then you should think of that that is a trigonometric polynomial with 31 random complex coefficients. Why 31? Because you're starting with frequency minus 15 up to 0 and then plus 15. So that's 31 free vectors in an orthogonal space. So we're talking about a 31-dimensional frequency space, or you can say it's omega 0 is the maximal frequency, then it's 2 omega 0 plus 1. And so actually I was just randomly choosing these coefficients, and then I was applying the inverse Fourier transform, which is just saying I could have taken a random linear combination of rows number 1, 2, 3 up to 16. Recall I'm starting with 0. And the last 15 rows and get some signal. Now, if you read the signal and you multiply with the Shah distribution, and the dem Shan is a separate M file, which says, well, my signal size, I keep it. The A is the same that we had before. Here you see it's 8 is the maximal frequency. No, 8 is the sampling rate. Sorry. 8 is the sampling rate. Yeah, so essentially the routine is made such that if I want to do a demonstration with sampling rate A, it chooses a function which is smooth enough so that this picture works out as it is. And the one is just saying, well, show me the picture. Otherwise, it's just demonstrating that I can reconstruct my X, my signal here, through this pathway with a reconstruction. So once more, we're starting with this situation. So maybe you say, I know the upper line. Or maybe let's do it differently. You know the upper line. You have generated these coefficients. You don't tell me, you even don't show me the picture, but you provide only these data to me. Now, because I'm familiar with the theory, I'm thinking, oh, what you're doing, you're multiplying this with a Dirac comp with lattice constant 8. So 8 is the lattice constant here. And if we do this, and this we want to understand also more closely, it means that we are periodizing the spectrum, so the Fourier transform, and we get 8 repetitions. You can also think, well, 8 copies are only possible at regular distance if the distance is 60. So the distance from the center of this spectrum to this first and second copy is always 60. In this way, we have equal distance or so. So yeah, well, it may be plausible that if you think of the distance of the centers being 60, that means this might be 10 or 12 or so, but okay. Now the question is, okay, you're giving me only the samples, and I know that this is equivalent to this. And so you were inclined to say, well, the way back from above to the lower part is, well, just cut out the frequencies. So I'm getting, well, a collection, and I need a lot of high frequencies because I really have jumps I need to represent these Diracs. But if I choose only the coefficients from inside this interval, then I will be able to recover, and we will see that this is just a pointwise multiplication with a rectangular function here, or maybe even better, with the rectangular function which is decaying smoothly outside, so a plateau function as I call it. And then we have to see what it means, how you can realize this on this side. But it will be a convolution, and that will give the Shannon sampling theorem. So it's kind of just this naive picture. So why is, I want to explain to you, why is sampling here corresponding to the multiplication? And we have already seen that this so-called convolution is the Cauchy product. And the Cauchy product is what you do when you multiply polynomials or when you multiply integers, more or less, as you learned at school. And of course, if you multiply polynomials by knowing the values, so on the Fourier transform side, you do ordinary multiplication. So it's plausible that you have to do a convolution of these discretized things. And if we know at the end that a Dirac measure, so a unit vector, gives a convolution operator which is a shift operator, then essentially you can get the Shannon sampling theorem from this. But let's go back, and this is kind of the goal of this representation. Let's go to the two-dimensional setting. So essentially, I will not do that demonstration. The analog of this situation would be here. Instead of band limited smooth signal, I would show you a band limited two-dimensional smooth function, which you can think of a landscape which is quite smooth, like the area where I'm living at home. Weinviertel is quite kind of rolling hills and very smooth in most directions, or it should be true in all directions. Then the two-dimensional representation would be something concentrated on the Fourier transform side. And then, of course, this would be done in a two-dimensional way, but still you can reconstruct this landscape from enough dense sampling points. But again, what I'm doing next is demonstration that the two-dimensional Fourier transform is also unitary. So I choose a two-dimensional random signal U. I just use capital letters now, and V. Then I take the two-dimensional FFT Fourier transform. Recalling, maybe that's another thing that I should demonstrate here. Recalling to you that of FUU is the same as multiplying from the left and from the right. Because, I mean, of course, good point to explain here. A triple matrix product in Matlab is realized by taking the bracket around the first two, then the second one. So what is the first doing? It's applying the Fourier transform matrix to a collection of column vectors, which is, of course, the same as FFT of U. So maybe I also do this so FFT of U is by convention the same as F with U. That's kind of because matrix multiplication works column-wise, and of course, the same is true for the FFT routine by definition. And so this is row-wise, and this is actually, you can say, multiplying with the transpose, but the transpose is the same as F, so it's acting on the rows. So the two-dimensional Fourier transform is the iteration in any order, either first rows and then columns, or first columns and then rows. And it's not surprising that if you're looking at the result, the scalar products are the same, well, again, up to some numerical error, which you can ignore. And the real part is exactly the factor n squared, which is a huge number. That's why I divided by n squared. And as you see, if you would take FFT two-dimensional divided by n, you would have a unitary change of basis. Now, What is the analog of our Dirac comp in the two-dimensional situation? Well, we are creating a lattice, and I claim that the orthogonal lattice is the one where you have now in each coordinate the complementary division. So the original one was a and n over a, and now we're doing it in this way. Actually, you could say that that's another way to create such a lattice. Maybe I'm showing you B is zeros of maybe I'm doing in the vertical direction from the beginning. B, so Dirac comp with distance B, so at rows number 1, 17, because B is 16, and I put a 1 here, and then of course I can demonstrate that this orthogonal, so the lattice is the same as the vertical Dirac comp with lattice constant B multiplied with the horizontal. So you think you have to recall that this is more or less matrix multiplication. And you see it's actually, I think it's probably implemented even in this way. So you're creating this standard lattices. Now the adjoint lattice is a little bit different, and it's due to the fact that you recall we're doing forward and inverse Fourier transform, so the normalization is different, and we are doing a flip afterwards. And that's just the orthogonal one would be lattice constant a n over a in the time direction and n over b in the frequency direction. Now we're flipping time and frequency also. So complementary divisors and changing the roles. Now, if you look at this, you see that again, up to the standard normalization, you can do just the FFT2, and then the adjoint, which is this here is, and actually that's how we compute it, is obtained by the symplectic Fourier transform, but with a normalization. Here you see it's just the density of the lattice that pops up. So if you're doing with this FFTS, you divide by the redundancy. Once more, redundancy factor 1.5 means we have here 1.5 times the number of lattice points in our lattice compared to n. So 720 or divided by 480 is the compensation factor. Now, see, I have to rerun these sections. The next one I want to tell you is I have a routine which is called create a circular filter. So we will use this maybe later for just for filtering, maybe in the two-dimensional setting. You also see it doesn't look so round. That this has to do with the fact that we have an integer lattice, and that we have Euclidean distances from the center, which in Matlab is 1, 1, but you should think of 0, 0, and therefore it's approximately circular. But of course it would be easier, maybe I should do this also, as insert filter symmetric. I think I hope this, it's available. And or maybe I'm doing something small, 24, 24, 3, and 5. And I show you this filter, maybe rectangular filter, maybe like this. Let's do this here. So this is quite easy to realize, or so it's just a scalar product of rectangular. So what does it mean? If you say it's a matrix of format 24 times 24, and with respect to the center, which is the first coordinate, so if I do the plot axis, you would see it's the plotting is adjusted, but the data are made such that you can use them in the correct way. So this is the position 1, 1, and now this is going. We have we're talking about the matrix now, and the matrix is described in size in terms of how many rows, how many columns is. So you're saying a 3 by 5 matrix has height 3 and width 5. Here we are saying we have to go first horizontally up and down 3 and so that if that would be a frequency filter, I would say its maximal frequency is 3 and maximal time delay of 5. So it's altogether we have 11. 5 plus 1 plus 5, 11 times 7, so 77 elements, and this routine is even counting it. Whereas here where I'm taking something with 50 to have a better number, and you're getting 705 elements or so. So kind of just to give you an idea. There's another way to represent it, and that's the radial weight function. And I've checked, it's not exactly the same or so, but maybe I should even also demonstrate this radial weight. So these are routines that are nice to have, but if I do the radial weight function of size n, that works as well. Yes. Then it's a function, maybe even with a color bar, which is extremely useful, of course. And the question is actually how to implement this, how to define it. And you will say, well, for every point in our rectangular grid, it has to give you the value of this. So maybe a radial weight is the radial weight of Fn. What is the minimum of radial weight? And if you're not going column wise but overall, then you should probably take this, take all the pixels, and that's this command. Let me see. And yeah, I see that this was the minimum is 1, so you're starting not with a distance from 1, but you're saying I'm at the origin is 1, I'm at the left neighborhood, so kind of what is the value be at number 2, which is, remember, we can also say we take at the one with distance 5 or so. So it is a matrix that we have plotted here. And you see number 2 is in Matlab order. So we are going down the first column, and number 2 is of course the pixel just below the 1, 1. So it's the position 2, 1. It's 1 down. The distance is of course 2. And if you go horizontally in this way, you have this, and of course you could even say what is their distance at I don't know 4, 4 or so. And then you would see some square root of the distance, and it would be really the Euclidean distance. Yeah. Okay, so this really looks very nice, and then of course you can say I take all the pixels where this radial weight is below some threshold. Here it was chosen 16. That's about what you have here, but I think it's the original command is different. And the other thing is, which you might want to look at, is how I was implementing the radial weight. First, I had a routine saying, well, go through all the pixels, but if you have 480 square pixels, that's quite amazing. Also, what is the distance of a point on the, we should think this is a two-dimensional torus, so left and right are glued together, then you have a cylinder, and then you glue together the ends of the cylinder. So essentially this point is the same as this point, and this point. So if you're leaving, the distance is growing in a linear way. But if you're coming here, the distance, of course, you look at the distance to this copy of this same point. So kind of it's like moving around on the surface of the Earth or so. If you're on this other side, at some point suddenly you're not saying I'm further away, but I'm coming closer from the other side. And so instead of doing it pixel-wise, what you have to do here is you have to calculate the horizontal and the vertical distance. So all the points in a given column have the same horizontal distance from the left side. So that's the difference in the x-coordinates. And that is just 1, 2, 3 up to the midpoint, and then it's going down in this way. But it's constant in this direction. So you compute the trivial distance on the basis of the coordinates as a head function, a Toblerone-like function in this direction. Then you add it on the other side, and then you take the usual Euclidean formula. The distance is square root of x squared, distance in the x direction plus distance in the y direction. So that's why it's a very cheap, very harmless routine, but still giving you something nice. Now, you see here as a demonstration that the circle, I have not checked the code anymore. I've been using this for a while. It's not so exact maybe, but they're about the same size. So that means that they're not exactly the same number.
Excuse me, may I interrupt?
Yeah, please.
It seems like the screen sharing has somehow got stuck.
Oh, okay. So new share. Thank you very much. For a long time, I hope not.
No, about a minute, I guess.
Okay,
I was not sure if it's only from...
I will share once more.
Thanks.
So yeah, thank you. You see now this colorful radial symmetric thing?
Nothing has changed.
It's still
stuck.
Yes. Yeah, okay. I do a new share. It's moving now?
No.
Okay. So maybe I take a break now